It's just that this happens to be a relatively long lecture, so we'll get through what we get through, and we'll talk about more on Monday. So, and it's fine because we are starting to outpace the assignment material slightly, but hopefully we'll be fine. So we were talking about plan costing, and the primary things we care about are number of rows that each plan node produces, the amount of disk I/O that's performed, because these are the primary costs that we care about. Clearly, you can sort of figure out if a plan eliminates work early by computing the number of rows and using that as a metric, and then also the amount of disk I/O. So those are both very helpful to identifying fast plans or slow plans. And we discussed the fact that you have to have statistics of some kind on your data if you're going to do this plan costing at all. And the quote-unquote holy grail would be histograms, but and most databases actually use histograms. There may even be better ways of doing this, but we're talking about very simplistic mechanisms right now because histograms take space and they introduce a number of challenges that you have to work through. So we just keep it very simple. Total number of rows in the table, number of blocks, min-max, and number of distinct values for each column can be very helpful as well. And of course, the approximations are usually inaccurate, but as long as we have this characteristic that slow plans cost more than fast plans, we're fine. We can just say, ooh, we have these two plans, we compute this magical cost, and it's like this cost for this plan is 231, and this other plan's cost is 95, so I'll pick the 95 one, and lo and behold, it's actually faster. Then we're fine. We're totally happy with that. And I mentioned this before, that if you look at Oracle's plan costs, if you look at Postgres's plan costs, they're just numbers. And I couldn't even tell you what the units are on those numbers. They just are some kind of metric that you can use for ordering plans approximately based on cost. Now, we also had a few more plan nodes that I wanted to talk about. Project. And in this situation, let's say that we have project of a simple column reference. So how many rows will this produce? Yeah, whatever number of rows R has. Because we're doing multi-set project, we're not in pure relational algebra land anymore. We left it long ago in like week 2 or week 3 of CS121. A number of distinct values you can also bring straight across, because I have constrained here this unrealistic constraint that the project is just referencing columns. And so you can see that if you're doing this statistics calculation in your plans, which some of you have noticed there's little to do saying someone would want to do this in the future, but I'm too lazy to do it, then you could just pull those column statistics across, and that would be an easy thing that you could do in those situations. Now, if you have an expression, you still have the same number of rows going through, but the number of distinct values and the min and the max values start to become much more complicated. And one option is to guess. The other option is to say, I don't actually know, which is probably what NanoDB would prefer, because generally it's designed so that plan costs can be absent because you guys have to add them yourself. So, and plan statistics as well may not be present if you haven't analyzed the table yet. So just not saying what they are because you don't know is probably the best approach. You could also imagine that if you knew some details about functions like sine and cosine, the min and max values will always be well known. You could do some things like that for some functions, but then there's plenty of functions where you really have no idea. I haven't seen sine and cosine show up in many database queries in a long time, so that tends to be pretty uncommon. Grouping and aggregation. So again, we can look at this and constrain it so that we can think about, well, what about this situation, which is an easy situation, or this other situation that's a hard situation? So the G sub i's could be column references or expressions, and the E sub i's could also be simple aggregates, sum x, min x, max x, or it could be something much more complicated. The first select that I have here is actually my favorite kind of thing to do in reporting queries, because you have, let's say, 50 gigs of data that you're trying to report on, so you're generating various metrics that somebody would be interested in seeing, and you could do multiple subqueries where you do an aggregate operation. For example, here I'm saying case when A is less than B, then 1 else 0. What we're counting up is the number of rows where A is less than B. And you could write this in a different way. You could say select count star from T where A is less than B. You could certainly do that. But the problem is if you have multiple aggregates like that that you wanted to compute and you have a giant table to scan, a lot of times it's better to just insert case when statements like this so that you can run your query once over the entire giant table and compute all your aggregates in the single pass. So you find ways of working your predicate into a case statement and then feeding that into a sum or something like that. And then that allows you to do your aggregate computations, all of them in one pass, as opposed to doing multiple passes. Like I said, I had a project where one pass over the data was about 45 minutes, and I certainly didn't want to have multiple passes just to compute some values. So anyway, these are certainly common situations that can occur. If we have simple column references in our grouping attributes, so all the G1 through Gn, how many grouping attribute columns or grouping attributes we have, they're all just simple column references. How many rows will the grouping operator produce? This is something that we can actually compute from our statistics. So we take in an input table. Let's say that we have statistics for that input table. One of the statistics is how many distinct values are there for each column. And we're also told that G1 through Gn are column references. So how many distinct rows will the G produce? Everybody here should know the answer to this. 1? Or are you saying I know the answer? Remember that we're going to get one group for each set of distinct values of the grouping attributes. So how many rows will this produce? Well, G1 has some distinct set of values, G2 has some distinct set of values, and so forth. We could just figure out the number of distinct values for each one of these grouping attributes, multiply them all together, and that'll tell us the distinct number of rows that are produced. And of course, the number of distinct values for each grouping attribute we can just pull straight across because it's a column reference. So this end of the grouping operation should be obvious and should be straightforward to compute. Number of distinct values of each column involved in grouping. Okay? Now, you can probably also see why I don't really require you guys to do this. I don't know if I'll be able to achieve this because I've been so tired, and when I'm not tired, I'm busy. So, but if I can, I would love for you all to have some kind of performance benchmark that you can tinker with, because we probably will have some spare time toward the end of the term. And going in and adding these kinds of statistics so that you can get better plan costs is a nice way of making sure that your costs are actually accurate and you choose an appropriate plan based on a particular query. So we'll see. I mean, you may have an opportunity to implement this stuff, you may not. If you have simple column references and simple aggregates, then you can also make some headway on some of these aggregates. So if we have count A, sum A, average A, so forth, where that's just whatever the expression is that's fed into the aggregate. So A doesn't mean that it's just a column. It could be whatever expression. We can just make a simple assumption that each group is going to have a distinct value for the aggregate computation. It's a simple approximation. May be completely inaccurate, but it certainly will work. You could do something like that. Min and max are interesting because, again, we could say, well, we're going to guess that it's just the number of groups. The number of distinct values of min and the number of distinct values of max will be the number of groups that we expect to produce. But you can actually do a little bit better in some situations. And the reason why is because if you look at count, sum, and average, they all can produce values that are outside of the set of input values. But if you have a situation like this where min is using, let's say that in this specific example, min is using a specific column, then you know min is going to select one of the existing column values. Max is going to select one of the existing column values. So in that situation, let me go ahead and throw this up. You could basically use that as an upper bound for the value that you produce. So you say, I may produce as many distinct values as I have groups, but if I actually have a smaller number of input values, I can use that as an upper bound. So I just pick the minimum of the two. Again, you could you could probably come up with better guesses for a lot of these different things. Okay. Let's see. Are there any questions about these? So I just wanted to throw those up there. As far as plan costing, I'm not going to spend too much time on this because we've already spent a lot of time talking about this, so there's not really a lot of point. The main thing that I want to, there's a few things that I want to sort of highlight from this slide. The fourth point here, most databases provide ways to give the optimizer hints about plan optimization. Oracle is particularly notable for this, where you can actually put comments in the SQL query and say, this is what I think you should consider when you're doing plan optimization. So you can give the optimizer hints. I can't remember if Postgres also can take hints, but you'll notice that a lot of the commercial databases can take hints because it may be that they just make bad choices based on whatever heuristics that they apply. So it's kind of an interesting thing that you sometimes run into when you're trying to do plan optimization. But that said, planners are getting so sophisticated that they're needing hints less and less. Hints were really important like a decade or 2 decades ago, but they're a lot less important now. Okay, and then the other most important point that's on here is that last point on the slide, which is that if you have inaccurate statistics, your planning is going to be terrible in general. So a lot of times when people are running into database query optimization issues and the optimizer is choosing terrible plans, the most important first step is to update the statistics and then see if the database is still choosing horrible plans. And then you can start figuring out what to do next. Okay? Any questions about plan costing at this point? Okay, so that's that. What we're going to talk about next is plan equivalence, and we'll start talking about how to build a planner that actually tries to optimize. And hopefully we'll get through all of this material today. So we had this query, and we had 3 examples of how we could evaluate this plan. Maybe these are 3 options that our database considers. So the question is, how do we actually know that these plans are equivalent? And we all, I think, have a sense of what it means for 2 plans to be equivalent. When we look at these 3 plans, we can sort of informally tell that they would all generate the same results. And that really gets to the heart of what it means for plans to be equivalent. So 2 plans are equivalent if they produce the same results for any possible legal database that you could handle. No matter what you do to the data, if you had these 2 plans and you ran them both on the same data set, they would come back with the same results. So that is plan equivalence. The order of tuples is not considered in this unless you have an order by, obviously. And this is kind of an important detail, and this is why SQL doesn't specify ordering of plan results in general, because we want the database to be able to make choices that may affect the output order, but generate more optimal plans. And you definitely notice this kind of thing. For example, nested loop join frequently produces tuples in no particular order. Sort merge join produces them in order based on the join attributes. And hash join may also produce results in no particular order, but definitely different than nested loop join. So we have these situations where choosing different join algorithms produces very different results, and you can identify that both in grouping aggregation, whether you do it by hashing or sorting, duplicate elimination, whether you do that by sorting or hashing, and so forth. So there's a lot of situations where the output results of 2 equivalent plans can be very different based on the algorithms you choose. Now that said, that's the implementation algorithm. That's one thing, but you also have just the set of plan nodes you use to generate the results. And that's where equivalence rules come into the picture, because they allow you to reason in easy ways about what plans are equivalent. So equivalence rules say, here are 2 expressions that are equivalent, or 2 forms of expressions that are equivalent. And what you can do in your planner optimizer is actually encode these equivalence rules in various ways to do transformations on plans to know that your planner will generate equivalent plans. And so that's something you can do, and then use plan costing to evaluate whether or not the other plan is actually better. So here's some simple rules. I have a select with 2 conjuncts, or 2 subpredicates that are ANDed together, and I can rewrite that as 2 selects. Now, we usually don't do it this way, but you could imagine situations where you do. Normally what we do is we like to collapse selects down into one select operation. But you could imagine a situation where we have a select with two predicates, and one of those predicates can be evaluated with an index, and so we'd like to move it so that we can use an index scan or an index lookup instead of just a file scan. So that would be an example. This is a very nice, simple rule. I think everybody can see how that works. You can reorder selects. So select theta 1 and then select theta 2 is equivalent to select theta 2 and then select theta 1. You can mix up your Cartesian products and selections to create theta joins. So here we have a situation where we do a Cartesian product, pass in, and then pass it through a predicate. We can rewrite that as a theta join. And you can see that we can also take a select that's outside of a theta join and push the selection predicate into the theta join as another condition. So these are both equivalent operations. And then you can also reorder the left and right side of the theta join, which, remember, was very helpful. Sometimes we'll have a situation where we want to put the large table on the left because the right table fits in memory, and we know that that makes our nested loop join go faster. Sometimes we want to put the smaller table on the left because we know that neither table fits in memory, and that will make our nested loop join go faster. So these are some various operations. Any questions about these? These should all be pretty obvious ones. They're not terribly complicated. Now, natural joins are associative, which is going to become really important because the order that we join tables together can definitely cause a lot of different consequences. For example, if we decide to join two giant tables together and generate another giant table and then join it against a third table that actually throws out most of the rows, that's stupid and that's wasteful. So what we could do instead is join a giant table against a small table, throw out most of those rows, and then join that result against a giant table and again throw out most of those rows. That might be a much more efficient way of doing things. So being able to vary the natural join order can be very helpful. Theta joins are also associated, but you have to think. Because we can move predicates around as long as we move them to places where all of their column references are still valid. That's really all we're doing here. So we have theta 1, theta 2, and theta 3. So like it says here, theta 1 only refers to attributes in E1 and or E2. So obviously we can't move theta 1 into the rightmost parentheses E2 theta join E3. That wouldn't make any sense because it would refer to stuff that isn't actually defined at that point, and so forth. So you have to think a little bit carefully when you reorder theta joins. You can sometimes move selects with theta joins. So is this going to work for any theta 1? Just any old theta 1? Or are there constraints on theta 1 here? Yeah, if theta 1 has stuff from E2, this is not going to be valid. Right? Does everybody see that? So in this case, we can move theta 1 in. We can wrap it around E1 as long as theta 1 only refers to attributes in E1. And so forth. So we have a situation like this. You can see that you could derive this equivalence rule, select theta 1 and theta 2, E1, theta join E2, from the first equivalence rule, as well as being able to break a selection of conjuncts into multiple select operations. So you could easily derive this equivalence rule from what we've already discussed. Now, that is just a tiny, tiny smattering of a few equivalence rules, because you could talk about grouping and aggregation. Remember, we talked about being able to push a predicate from outside of a grouping and aggregation operation to the inside of a grouping and aggregation operation if the predicate satisfies certain constraints. Like it only eliminates whole groups was the rule that we talked about in CS121. That was on an assignment. But you have outer joins, you have projects. For example, if you have a series of projects, a lot of times you can collapse all of those down into a single project. There's an equivalence rule for that. And other things as well. There's a lot of different examples that you could use. I should actually give you that section of the book again. It was on the CS121. It was in the CS121 material, but it's really nice to have that collection of equivalence rules to look at. So yeah, this was the example here. You have a selection outside of a grouping and aggregation. It is equivalent to putting the selection inside the grouping and aggregate, but only if theta eliminates entire groups. So like it says here, as long as theta only involves attributes in A. If it involves any attributes outside of A, now you start having trouble. But what could you do? If theta involves attributes outside of A, what you could do is take that select theta and maybe break it up into multiple selects, because if theta involves conjuncts, you can separate it into two. And then you could push some of the selection in, and you could leave some of the selection outside. So there's a lot of options. When you have these situations, you can always like, well, do I have this case? Do I have that case? And you sort of start to see that, well, the more intelligent the programmer is that is writing the planner, the more intelligent the planner gets, the more intelligent the database gets. And so that's why, for example, you'll see databases get better and better at things like query decorrelation and doing, flattening queries and stuff over time, because they're adding more and more intelligence to the planner. This is also why NanoDB, who has a lot of their planner working already? Can anybody do joins yet? Okay, well, get working, guys. You should be able to do that pretty quick. But you'll notice that there's a lot of plans for which it'll run very slowly, and you'll even see that in the third assignment, because you'll try that and you'll start seeing where it's slow. And then you'll make the planner smarter, and it'll be able to do more things. So it's kind of neat that you can add, as you add more heuristics and add more rules, they get more and more intelligent. Now here's another rule. Outer join, you do a selection outside of a left outer join, and you can push that selection down to the left side as long as the theta only involves attributes in E1. Now, can you, I won't get ahead of myself, but this is very important. Outer joins greatly complicate these rules. So as long as we have inner joins, we're very happy. The database has a lot of flexibility. But if we have a situation where there are outer joins in the picture, then we start having a lot of complexity. But anyway, we'll talk about that in a moment as I show you some bad equivalence rules. But we have this situation, remember, we had the select at the top. We can go ahead and move part of that down. And it actually involves a couple of equivalence rules, like I was saying, that we can take a selection and break it into multiple selections, and then we can push down a selection onto the theta join, as long as it only involves attributes in E1 and E2, which we have in this situation. T1.a equals T2.a. And then we can take this and apply another equivalence rule to get to the situation where T2.b greater than 5 is actually enforced on the file scan or the index scan as opposed to on the top select or on the theta join. Okay? But you can see you could generate a lot of other equivalent plans as well. Okay? Any questions? I'm trying to think if there's anything else I want to say about this. Oh yeah, the one thing that I would say is you could imagine creating a planner. Like if we had a really good language for doing symbolic processing and manipulation, like anything other than Java, then you could probably do something where you encoded equivalence rules as patterns and then use those to try to match subtrees on your tree and then apply the transformation very mechanically. And that would be really cool because then you could add more and more equivalence rules and it would just try them. But Java's not that great at doing this kind of thing, and so you find that you manually hard code these kinds of transformations as heuristics. So it tends to be that these equivalence rules inform the implementation, but the implementation doesn't explicitly state them, except maybe in comments. That would be the only place that you would actually do that. Okay, outer join transformation. So I was mentioning that outer joins start introducing landmines into the landscape. So we have this example. Remember that we can push a selection down to E1, E1 being the left side of the left outer join, if the predicate only involves attributes in E1. Are we allowed to do this? Yes, no. Anybody remember? This was on a CS121 assignment, so you should remember. Yeah. You're not allowed to do this one. Hopefully you can remember some examples. So here's an example. So let's say that we have R with A and B attributes and just one row, 1 and 2. S with B and C and one row, 2 and 3. So what is the left version going to generate as its output? E1 left outer join E2. Well, in this case, it's R left outer join S. We actually have a matching rows, so we generate a result 1, 2, 3, and then we apply this predicate C equals 1 and C is 3, so that gets evicted. So we have a situation where the left expression is going to generate an empty result set. Now, what's the right one generate? Well, we apply our selection early, and 3 is definitely not equal to 1, so the right subplan, or the right subquery, generates an empty result set, and then we left outer join that against 1, 2. What do we get? Well, now we get 1, 2, null, because the left row is included, but it's null padded. So these two expressions do not generate the same results, so they are not equivalent. This, again, must inform your planner, because you have to go in there and say, well, am I actually allowed to push this predicate down to this part of the subplan? And it turns out that you can basically push down predicates in outer joins as long as you're only pushing them onto outer sides of the outer join. If you're trying to push it onto an inner side, then you're not allowed to do it. And assignment 4 has much more detailed discussion of this, because your join planner should be able to do that. Okay, so you need to be careful about this, mainly because all of our equivalence rules for natural joins, theta joins, it's like, oh yeah, you can mix and match and move stuff around, and it's so powerful and easy. You basically can't assume anything once you start introducing outer joins. You have to start looking very carefully at what you're allowed to do. Here's another one. Can I evaluate the left side of 3 outer joins first, or the right side of the 3 left outer joins first? Are they equivalent? And again, we're in a situation where if I'm asking the question, it's probably the answer is no. So this is actually not allowed. And again, you can look at a simple example, RAB, SAC, and TAD, where we have 1, 2, 2, 3, and 1, 4. The left one is going to generate, let's see, we have a left outer join, so we have 1, 2, null, and then we join that against 1, 4, so we're going to end up with 1, 2, null, 4, I believe. Correct me if I'm wrong. The right one, we're going to end up with 1, 2, no, I'm sorry, we're going to end up with 2, 3 being joined against 1, 4. So we get 2, 3, null. And then that gets joined against 1, 2. So we end up with, I think, 1, 2, null, null. Let me see what I have here. Oh yeah, so I have those things. Yeah, so you end up with 1, 2, null, 4, and 1, 2, null, null. Yay, I can basically do what a database says. Okay, so everybody see? So these things are not equivalent, so when we're doing our join ordering and trying to come up with an optimal plan, we can't just assume that outer joins can be rearranged, which is really, really frustrating. Now, what's interesting is that different databases actually have different ways of figuring out join ordering with outer joins. It's kind of funny because one database will try to encode equivalence rules and say, well, I'm not allowed to transform this, but I'm allowed to reorder this other stuff, so I will only constrain myself to equivalent plans. There's, I believe it's MySQL, but I don't want you to quote me because I may be wrong, that actually generates all possible arbitrary orders, and then it sees if it's valid or not, if it would violate the equivalence rule. So basically, it generates a possible join order, and then it's like, oh, but there's outer joins, so it throws it out. And then it generates another one. It's like, yeah, this is okay with the outer joins, and it keeps it. So there's different ways of tackling this problem, but you have to be very careful when you're reordering outer joins that you end up with an equivalent result. Okay. For example, you can always, of course, take E1 left outer join E2 and flip it and do E2 right outer join E1, and then put a suitable project on it. So there's things that you can do to reorder things somewhat, but you can't just do no holds barred whatever order I want like you could with natural joins or theta joins. Okay, so enough of that. I will not belabor that any longer. So, given that we do have a general understanding of how to map these queries to plans, and I am ignoring subqueries and the select and where clauses, I don't want to make any promises, but I'm going to try to revisit that topic on Monday or Wednesday, depending on how much we get through today. Yeah, and we understand how to implement plan nodes, and we have a lot of different ways that we can evaluate that we can evaluate a given query, so we can generate many plans for a particular query. So the question is, how do we find an optimal plan? How do we figure out the best way of executing a particular query? And like I have on the slide, basically everything relies on equivalence rules because I have to know what other valid alternatives do I have for evaluating a particular query. So we will try to discuss select and where clauses because there's some really neat things, but we definitely won't discuss it today. Now, one option is definitely to just try to make the planner as smart as possible but encode all these rules and never look at plan costs. There are a few databases that do this kind of thing. It tends to be a way that many early database planner optimizers do things. I mean, early in the products or the project cycle, because who has time to write the plan costing yet and the plan transformation? So you start out with heuristics, and it gets you a certain way down the field, and you just sort of hope that these rules are correct. So here's a simple example of a heuristic. Perform selects as early as possible. Another heuristic would be perform projects as late as possible. Perform sorting as late as possible. These are example heuristics that you might employ. And you could get much more complex where the heuristics involve equivalence rules, like always push selection through group by and aggregation if you possibly can. That would sort of be a special case of perform selects as early as possible. And we could do that. It would distribute our predicates reasonably well, but it's not a perfect situation. It's not a perfect solution. Okay, we had this situation. We have these conjuncts, t1.a equals t2.a and t2.b greater than 5. And what we're going to do is just try to do those selections as early as possible, and we end up with this plan. So that's kind of nice. We have a theta join with an equality, so now we can use an equijoin algorithm like sort merge, or we could use hash join to do that theta join as efficiently as possible. And hopefully, if T2 is large enough, we can use this predicate to reduce the number of rows that have to be considered, and we'll actually be happy. Now, this, again, would probably work in a large number of situations. But there's also situations where it breaks down. And this is the sort of the limitation of heuristic optimizers, is they can run into these cases where it's like, oh, this situation actually causes my heuristic optimizer to generate a bad plan. And so, again, this is where hints come into the picture, because you can tell the database, actually turn off this heuristic or turn off that heuristic for this query. So the scenario is T1 is a small table and T2 is very large and has an index on A but no index on B. Now we haven't talked about indexes yet. And just discussing what we have discussed so far about join algorithms, you might look at this and say, well, let's assume nested loop join. And what I want is for the small table to be on the right, because I can fit it into memory. And then I have my large table on the left, but at least I'm eliminating a bunch of disk seeks because I only read the small table once, and then now it's in memory, and I can just scan through the large table and do this. Well, there's something we're not taking into account here, which is how many rows do we expect will actually be identified by t2.b greater than 5? What if this is just some enumeration and maybe the b values range from like 1 to 7 or something like that, and there aren't a whole lot of rows with values 6 and 7 in our table T2. So even though table T2 is really large, we would get a huge benefit out of using the index to look up the specific rows. Well, there turns out to be an optimization for nested loop join where you can actually put a table with an index on the inner side or on the right side and use index lookups to identify rows. You may be familiar with this from MySQL. Well, in that situation, we do want the small table on the left and we want the table with the index on the right. And we want to apply that predicate up in the theta join, not as early as possible. That's kind of one example scenario that you could have. You come up with a number of other scenarios as well. Okay. So there's some interesting situations that you could have. Actually, I think I completely misexplained that. But anyway, yeah. Oh yeah. So this is just like if the index is on A, you could still use the index to look up rows on the scan. Sorry, I bollocksed that. But you can sort of look at the slide and see exactly what's going on. Okay. So that's heuristic optimization. It's okay. It's great. I mean, it's easy to do. And in fact, what you're probably going to do for, I mean, there will be some heuristics in the planner optimizer that you write for assignment 4. But in assignment 3, you probably won't have any heuristics, and you'll see sort of like, oh, it's just pretty naive. But you do get a benefit from computing cost, because then you can use that to tell if your guess is actually a good guess or not. And you can throw out the bad guesses, and that's kind of a really nice thing. So that's cost-based optimizers, where you can look at a whole bunch of different plans, you generate as many as you can, and you choose the best one based on performance. It is tempting to generate all possible plans, but the problem is this search space is pretty freaking huge. And even if you just look at join ordering, you know, all the possible ways of joining a set of tables with binary join operators, that by itself is really huge. And anytime we're trying to generate an optimal plan, we're not spending generating results. And that's what the user really cares about. So you want to spend a little bit of time planning and a little bit of time evaluating. So even if you don't come up with the best plan, if you come up with a good one, it's okay. So like it says here, join is a binary operation. And let's say we have n relations to join. And R1 theta join, or R1 natural join, whatever, it doesn't matter. R2 may have a different cost than R2 join R1. This is the number of different orderings you can end up with. And I'm not going to go into the derivation of this, but there is a practice exercise in the textbook. And the answers to the practice exercises are available online, so you can go look at the answer for this practice exercise and see how they derive this result. But you can see it starts ballooning immensely. Now, are you frequently going to have 7-table joins? Probably not. I have run into them from time to time. It tends to indicate an over-normalized database. You know, you want to definitely avoid having that many joins, but it happens, and so you have to be, you know, when you're writing a planner optimizer, you have to be sensitive to those kinds of situations. You don't want to have the 7-table join, and it spends like 45 minutes considering join orders. Okay, so this is any arbitrary join tree. If you decide to do this, it is possible, but you have to be very careful. Like it says here, you have to think about, well, how much memory am I going to take to generate all of these plans? And there's things you can do like memoization. I generated a subplan. I'm just going to keep reusing that subplan and its cost when I consider other plans that use that subplan. There are actually databases that do this. SQL Server is a great example of a database that actually does this. These two projects, Volcano and Cascades, are research projects. And if you get on the ACM website, the ACM library, you can search for them and you'll find papers that describe how their planner optimizers work, and they basically try to do as exhaustive a plan enumeration as possible. But most planners don't do this because it's just too expensive. And there's a saying, don't let the perfect become the enemy of the good, which is one of my favorite sayings because it can totally inform you when it comes to software engineering or many other parts of life. Just try to make sure you have a good strategy or a good approach. And if it's not perfect, well, life will go on. So we try to constrain the search space in various ways. One option, or one way that is very common for constraining the plan search space is to only generate left deep join orders. So like I have here, you have n tables. Well, what I will always do is have joins that go off to the left, and I'll have tables hanging off the right. Now, if you had a select subplan, you might have that as a right node, if your planner wasn't smart enough to combine that in some way. But in general, my joins are only going to have a subplan on the left, and if they can, tables on the right. And you'll notice, like I say here, for nested loops, this is really nice because now you don't have to mark and reset, or primarily just reset subplans and reevaluate them if they're on the right side of a join. So this is kind of nice. If you consider MySQL, that's all it's capable of doing is left deep join plans because it represents the joins as a sequence of elements in an array, and that just specifies the join order. So it only considers left deep join trees. And so that reduces the number of possible join orders to n factorial, which is much easier to consider than the other expression that I had on the previous slide. And so you start seeing more heuristics being applied. And so this is called guided cost-based plan enumeration because we are using some heuristics to consider what might be good possibilities. We're not just exhaustively considering everything. Now, when you have joins of multiple tables and subqueries and select and where clauses, basically this is the approach that many planners take. Try to do high-level transformations on the abstract syntax tree so that we can flatten the thing as much as possible. Then we apply heuristics that will allow us to improve query performance in most situations, but these heuristics may be wrong sometimes. So we use costing where we can to pick, to see if a heuristic applies. Okay, so we can still do that. And then we focus on the join order in particular. And that join order will actually have a pretty profound effect. So if we choose a good join order, then that gets us like 95% of the way there. And so this is what most planner optimizers actually do. High-level SQL optimizations, heuristics to figure out where to put stuff, generate a couple of equivalent plans, pick a good join order, see how much that costs. And then you have various variations that they will try to see if they can improve this. Okay, now how you actually do this is there's a couple of different ways to do this. Like I say here, a bottom-up approach or top-down. Bottom-up tends to be based on dynamic programming because we generate the smallest possible answer, record its cost, and then we try to generate larger answers based on what we already know to generate an optimal answer at each level. So like it says here, you decompose the plan into the smallest possible subplans, choose the best implementation, typically based on either heuristics or cost. You can actually use cost as well at this point if you want. And then as you build up larger subplans, you have memoized these earlier steps, and so you can just refer to them to see, well, what would be the best way of achieving the next step given that I know the best step at the or the best approach at the previous level. And like I say here, this does generate very good plans. But there is an issue that is basically a greedy approach, and so you may constrain yourself from being able to take advantage of a less optimal lower level solution that actually gives you better high level optimizations. So keep that in your mind because we'll talk about that in a second. Now top down is interesting because you can actually figure out what your best plan cost is so far. Like it says here, branch and bound. So you figure out some plan that you think is good using heuristics, and you know its cost. So we call that cost C, and then we can start generating alternatives, and if anything is more costly than our cost C, we throw out the plan. We don't even consider that approach anymore. So we're sort of cutting off possible branches to explore. And if we find a better plan, we lower our cost C. So this allows us to basically constrain the search space so that we can figure out what would be a better approach. Yeah? Yeah, it definitely can be unfeasible to be exhaustive. Well, even doing simple things like figuring out where all to put selections, you can get pretty expensive. And we won't see that in our queries because our queries will be pretty small. But when you're talking about a reporting query that involves 5 or 6 tables and has 3 or 4 nested queries in it, then the search space can actually get quite large. And so those are the situations where you need to be more careful about trying to exhaustively enumerate everything. Yeah. Thankfully, the big queries are not very common, but they're common enough. One of my goals, one of my long-term goals, is to be able to run this performance benchmark on NanoDB called TC. Did I get this wrong? No, TPC8. It's too bad that TCP and TPC are so close together. TPC is the Transaction Processing Council, and they basically come up with performance benchmarks for database vendors to run so that everybody has a single standard to check their database against that's not generated by a biased company. And you frequently see, for example, performance benchmarks that are like people will hard code their implementations to the benchmark to try to look good, but what a terrible thing to do. And you see that in graphics, you see that in scientific computation, you see that in a lot of different areas. So having this separate group come up with benchmarks is really cool. I want to do that with NanoDB eventually. Some of those queries are quite complex. And it's basically like an order database. So you have orders, customers, regions where customers are, you have order line items, and an order might be 20 or 30 items, or it might be smaller, it might be larger. And even just that simple database, you have all kinds of interesting questions you can ask. How many orders are there in this region versus that region? What's the top region based on profit of the revenue of orders and so forth? I mean, there's all kinds of things you can ask. And in those situations, even you would have a pretty large search space if you tried to exhaustively enumerate everything. So, there's another interesting benefit of this branch and bound approach. It allows us, we can use our value C, the cost of the best plan we've found so far, we can use that to figure out whether or not we should continue trying to optimize or whether we should just stop. Because if we have a simple plan and we haven't thought very hard, and the cost is low enough, we could just say, you know what, forget it. We don't need to search anymore because we actually have something good enough. But if the plan cost is really large, then that's indicative that we need to think harder for longer, and so you can keep looking. So it's kind of interesting that you can use this cost to figure out whether or not you can stop trying to optimize or whether you should keep going. Okay, so optimizing join order. I'm trying to think. Yeah, so R1 theta join through R5, we need to figure out an optimal order. And so for n is 5, it's just n factorial. That's not too many. You could probably enumerate these relatively easily, but we can even do this more efficiently using dynamic programming. So let's say that we already know the optimal join order for R1 through R3. Well, now we just have to consider R4 and R5. So basically, you can, again, memoize as you go and store, like, well, what's the optimal way of joining R1 and R2 and R1 and R3 and R1 and R4 and R1 and R5, and then you can use that information to look up things and sort of compose these things and generate more sophisticated plans. Okay, so I think I have a quick way. We'll talk about this and then we'll go ahead and wrap up. So this would be finding a join order with dynamic programming. So we figure out for each leaf in our join plan, what would be the best way of accessing that thing? And so it may be here we actually look at our predicates and we say, well, we've got a predicate here that we can take advantage of an index, so we'll go ahead and apply that, generate a small number of rows using our index optimization and so forth, and we'll compute costs for all of those things. And we save that somewhere to say, here's the optimal way to access each thing. The next step is to figure out how to join all pairs of these things. So we go through, exhaustively enumerate all pairs, and we figure out the best way to join each one of those. Here we use sort merge, here we use hybrid hash join or something like that. We figure out what predicates we can take advantage of in each step. Once we have that, we take the pairs of tables and we take the individual table and we figure out how to join 3 tables, all combinations of 3 tables, and then all combinations of 4 tables, and so forth, till you get to all combinations of n tables. Well, in fact, you get one optimal way of joining the n tables. Okay? So that's a bottom-up approach. Let me see. Now, left deep order, I'll just mention this and then we'll wrap up because I don't want to go long. We've been going long a little bit much. If you want to limit your planner to only generating left deep orders, you'll see that the bottom-up algorithm is very easy to do that because I have n minus 1 tables that I need to join, and then I have the single table, And so you can use that to generate joins that are left deep very easily. You just make sure that when you're adding something in, you always put the single table on the right. Okay? What you'll notice in the top-down approach, and I'll just give you the punchline, we'll talk about this more on Monday, but the top-down approach actually makes it a lot harder to generate left deep joins. So we'll talk about that next time. Are there any questions? Okay, so I'll see you all on Monday.